Hello people, this is Phil. I'm going to take a little break from my x86-64 assembly language programming videos and introduce this new project, building an assembly or building a virtual machine from scratch. The purpose of this project is to illustrate how a computer works. So we're going to be able to explore this by creating a very simple machine or computer on our own. And so instead of going heavily into theory at first, what we're going to do is build a minimum viable virtual machine right off the bat. And so we're in our workspace. So if you have your workspace set up, it's empty right now. And we're going to create a file and we're going to call it, we're going to actually create a class, a stack virtual machine class, because I like stack machines and they're very simple to implement. So our virtual CPU will be a stack machine. So we're going to create stack VM.cpp. Actually, let's start off with the H file. And what we're going to do is a little bit of housekeeping and create something called stack VM H. Okay, now we'll do some includes, and what we're going to do is we're going to include for now IOStream. Since we want to see what's going on inside our virtual machine, we're going to want to print some stuff out. And then we're also going to include vector, because we're going to use vector a lot. Okay, so now that we've got those out of the way, let's actually define, let's do our type definitions. We'll do type definitions. And for right now, we're only going to have one type. So we'll do a type def, and we'll do int32, and we're basically creating a signed integer of 32 bits size, and everything in our virtual machine, at least for right now, will be 32 bits in size for simplicity. Then we'll go ahead and create our class. We're going to call it stack VM, and let's go ahead and create some registers for ourselves. So even though this is a stack machine, we're going to have some registers that will store some information for us. So we're going to have a program counter, and we're just going to start it off at address 100. We'll probably end up changing this later. Then we're going to have a stack pointer, which will start at address 0. And then let's create let's create our memory. So this will be the memory that our virtual CPU will access. And then we're going to create a couple more registers. These aren't typical in normal virtual machines, but we're going to create them to create some simplicity for our machine. We're going to have a type and a data register. And then we're also going to have a register that tells us whether we're still running. So all of these things are private. And let's now create a let's create some functions. So let's create some private functions that we're going to use for our stack VM class. And one of the things that we'll need to do, I'll explain a little bit of this later, but we're going to need a getType function that will be able to take a token from our machine, or an instruction. Actually, let's actually just call it an instruction. And we'll need to be able to get the the type of that instruction. We'll also get the data from our instruction, and the way that our instructions will work is we're actually going to combine our data with our instructions, and we'll illustrate that a little bit later. The other things that we'll need to do is a CPU essentially runs in an infinite loop, and it performs 3 operations over and over until it halts. And those 3 operations are fetch, decode, and execute. Now we're not going to put all of our execution code inside execute. So what we're going to do instead actually is we're going to have a nice little helper function for right now called doPrimitive. And that's how we're going to put a lot of our code there for executing instructions. Now let's create some public members. We'll do public functions, and those will be a constructor, and we'll also need some way to run our machine. So we'll have a run function, and then we'll also have a load program function, which will allow us to initialize our memory, because we're going to need some way to initialize our memory for our virtual CPU to run. Then at the end here, we're going to create an indif, and that is our header file. So let's go ahead and create our CPP file. And in our CPP file, we're going to include our stackvm.h file. And then let's see, let me take a look at my notes, because this is a little bit more complicated project. So we're going to have our stackvm, and then we're going to implement our functions. So we're going to have our, let's go ahead and implement our constructor, and all it will do is reserve some memory for us. And we're going to go ahead and reserve 1,000,000 words of memory. We may use more in the future, but for right now that's pretty good. Then what we're going to do is let's do our get type function. All right, 32. I'm going to have an instruction, and what we'll do is we'll create let's create a type, and we're actually going to use a hexadecimal value here. 2, 3, 4, 5, 6, 7. There we go. Essentially, since everything is 32 bits, every 2 characters is a byte in hexadecimal. So we've got 1 byte, 2 bytes, 3 bytes, 4 bytes. So we've got 32 bits. Now, let's do type. Let's actually do something with this. We'll do type, and we'll bitwise AND it with our function, and we'll shift it 30 bits. And so what we're going to do here, now I should explain how our instructions work. The way our instructions will work is every instruction has essentially a 2-bit header, which says what sort of instruction it is. And the way we're going to encode our instructions, in fact, I should probably maybe put a There we go. Instruction format. So we'll have a header, which will be 2 bits, and then we'll have a body, or data, I guess, which will be 30 bits. And our header format will be, if it's a 0, then it's a positive integer. If it's a 1, then it will be a primitive instruction. And if it's a 2, it will be a negative integer. If it's a 3, right now that's undefined. So we'll say undefined. So that is how our instructions will work. Whoops, actually, there we go. In fact, whoops, yeah, that'll work. So that is how our instructions will work. Our instructions will have 2 bits in the front, which will tell us what type it is, and data, which is 30 bits. Now there is a reason behind the madness for this, is it makes our instructions fairly compact. And then the reason we have these numbers, say 0 for a positive integer, is suppose the first 2 bits are zeros, then the other 30 bits are our number. Well, then if we look at that as just a 32-bit integer, it will actually be a positive 32-bit integer. And this negative number, remember 2 in binary is 1, 0. So if the first 2 bits is a 1 and a 0, the first bit of our 32-bit instruction is a 1, we can interpret it as a negative number. So that just makes things very convenient. Now, having a 1 in here, we've defined that to be a primitive instruction, and that will be an executable instruction that we will work on. So let's go ahead, and that will make more sense as we go along. So let's go ahead and create our other function called getData, and it will also take an instruction of 32 bits, and it will have data, and what we'll do is we want to take 30 bits of it. So 1, 2, 3, 4, 5, 6, 7. I think that works. And actually this needs to be a hexadecimal number. And let's see, what do we want to do with it? So our data will actually be data with a binary and with our instruction. Okay, then, oh, we also want to return, so let's do that. We'll return our type, and at the very end here we'll return our data, which will be 30 bits of our instruction, the bottom 30 bits. Now let's go ahead and create our main functions to run our program. So we'll create our let's see, oops, we'll create our fetch function, and our fetch function will simply be incrementing our program counter. That's simple enough. Then we will have our decode function. That's a little bit more complicated. What we're going to do is to decode our instruction. What we'll do is set our type. Remember, this was our TYP is a register, and we're going to fill it with the information get type, and we'll look at our memory at our program counter. So we're looking at the instruction. We're essentially getting the instruction from memory and getting its type. Oh, this needs to be like this. Get data. We'll look at the same instruction at the program counter, and that's it for decoding our instruction. Now we need to execute our instruction, and this is where we have to do a little bit of decision making. So we're going to say if the type of our instruction is 0, which means if it's a positive integer or if it's a negative integer. So if our type is 2, we want to we actually want to integrate increment our stack pointer, and we want to set the top of our stack to data. Now this is a little bit different from normal assembly languages and computers that have a stack. Normally the stack grows downward. What we're going to do is our stack is going to start at address 0 in memory and move upward, at least for now. And it's an interesting way of looking at it, a little bit different way, but it will work. So then otherwise, if it's not a number, we'll do a primitive. And that's it for our executing the stack. Now, for the real meat of our program will be this do primitive, which in a CPU would be, I guess, the equivalent of the control mechanism. So we're going to do that. We're going to do stack VM, do primitive, and we're just going to have a big switch statement on our data, and we're going to do a case. Actually, we'll have a case statement. So for 0, so now we need to design our instruction set, right? So our instructions will, if the first 2 bits are a 1, the data of our instruction will actually tell us what type of instruction that we have to run. And so this is sort of arbitrary. We can set whatever numbers you want. You can change yours to whatever you want them to be. But for right now, what I'm going to do is 0 is going to mean halt in our instruction set. And what we're going to do is we're going to show how this is working. We want to show the inner workings of this. So for now, we're going to say that we're going to print this out and tell ourselves when we're actually halting. And what we want to do is we want to set the state register, the running register, to 0 to tell us that we're not running anymore. And then we want to break, do a break on our system. So actually, maybe that should be there. And then we'll do a case 1, and that is going to be add. And the way that we're going to add things is we're going to print this out first. We're going to say that we're adding, and we're going to show the numbers that we're adding. We'll get our items from memory, which we get from our stack because everything is put on the stack. And those are the 2 items from the stack that we'll be adding together. And then, okay, now we need to add them together. So we're going to actually get our memory, address from memory. We're actually going to subtract 1 from it because remember, our stack is growing, and when we add 2 things together, we're going to pop 2 things off the stack, add them together, and put the answer back on the stack. So the way that we do that efficiently is to essentially take the piece of the stack that's right below the top of the stack, and we're going to set it to our answer. And our answer is our memory at stack pointer -1 plus our memory value at the stack pointer. And then we're going to do a break there. And then what we'll do is we'll just leave that for there. So that's the minimum that we need. Oh, whoops. That's the minimum we need to create our system. So now we've got a system that can add. Now, let's see, what else do we need? We need to be able to run our program. So we're going to create stack VM run, and what we're going to do is remember up above here, the first thing we do in our system is we fetch an instruction, and we fetch an instruction by incrementing our program counter. So the thing is when we load our program, we're going to actually load it at our program counter. So what we need to do is to bootstrap our system, we need to set our program counter to be 1 minus whatever it was before. So that way the first time we fetch, it's actually on the count that we want it to be. So what we're going to do is we're going to do while our processor is running. Oops. While our processor is running, we're going to fetch, decode, and execute our instructions. And then let's go ahead and print out our top of the stack, which is our the value of our memory at our stack pointer. Okay, so that is how we run. The only thing that we have left to do is loading our program. So that's what we need to do. Let's load our program, or create our load program function, and it's going to just be a vector of 32-bit integers. And we're going to use a for loop, and our program, for our program size, we're going to loop through, oops, and all that we're going to do for that is set the value of our memory. We're going to start at our program counter and add I to it, and then set it to our program instruction at that location. So that is how we load our program into memory. So now we've got a stack class implemented. Alright, so let's create a program to actually utilize this stack machine that we've created. So let's do vim main cpp. And first thing we'll do is include stack vm.h, and then we'll create our main function. Let's create a stack VM, just call it VM. Then we'll create a vector, a standard vector of 32-bit integers, and this is going to be our program. And what we're going to do is we're going to put 3 and 4 on the stack, and then we're going to give it an instruction. Let's see, 0 is halt and 1 is add, so we're going to do we'll do add, and then we'll do a halt instruction, basically. There we go. And then let's load this program. So into our virtual machine program. And then we can run our virtual machine. And then let's return 0. Okay, so now we've got a program created. And don't worry if you don't understand completely how these hex numbers work. I'm going to go over that next time. Let's go ahead and build a makefile for our system. So now we'll be able to compile and run our program. So the first thing that we'll do is we'll create, let's do a C flags, and we're gonna use the C++ 11 standard. Then let's create an all label, build stack VM, and then stack VM will be stack VM.o and main.o. And then let's see, we're going to have our compiler, whatever our compiler is using, and we're going to have our C flags. Stack VM main.o, and whoops, our output will be stack VM, so our executable will be called stack VM. Now we need our main.o, which means we'll need main.cpp, and we'll use our compiler flags. And then we'll compile main cpp. Then we'll have stack vm.o, which needs stack vm.h, stack vm, .cpp, and then we will also use our compiler and our compiling flags, and stack vm.cpp, and then we'll create a clean function which will just remove all our .o files and stack VM. Alright, so that's our makefile. So let's go ahead and try to make this function. So we've got some errors already. Oh, I bet. Let's see. So let's take a look at stack VM CPP line 41. So it says that do primitive does not exist. Let's see. Oh, that's because we're missing a colon. Okay, so let's try that again. So do primitive was not declared in the scope. Do primitive. Let's check it out. Ah, primitive is not spelled correctly. There we go. So now we have our stack VM executable. If we run it, we see that our top of the stack was 3, then our top of the stack was 4, then we add 3 and 4 together. Uh-oh, looks like we have another error. Didn't actually add 3 and 4 together. Top of the stack was 4 at the end, so we're going to have to fix that. So let's go to our, let's see, stack pointer. Let's see, I bet we need to change our Yes, that's right, we need to change our stack pointer. So let's go here. Stack pointer actually needs to decrement here. And the reason for that is our stack got one smaller. So the top of our stack is now one less, or our stack size is one less than it used to be. So let's make our program again. We'll run stack.vm, and now we have 3 plus 4 equals 7. So I know this was a very quick introduction. I didn't explain too much, but now we have a minimal virtual machine that we can play around with and add to. So next time we're going to explain, or I'm going to explain a little bit more about how the instructions work and how we're going to improve our virtual machine. Thanks for watching. Till next time.